Hello everyone, thank you for attending this webinar. I'm Shuhua Hu. I'm a principal research scientist at Certara. The objective of this webinar is to introduce gammaDelay function that was recently implemented in PML to model delayed outcomes through gamma-distributed delay. PML is a pharmacometric modeling language behind the Phoenix NLME. It's also the modeling language behind our new product, NLME. So the gammaDelay function can be used for both products. In this talk, first, I would like to give some background and motivation on using distributed delays to model delayed outcomes. Next, I will explain why we recommend using gamma-distributed delay instead of widely used transit compartment model to model delayed outcomes. Then I will explain how to implement gamma-distributed delay in PML. Finally, I will demonstrate how to extend a published transit compartment model to a gamma-distributed delay model and how to implement this model. Delay often occurs in PKPD studies. For example, delay may arise during PK absorption phase as it takes time for drug to be transported from the depot site to the central compartment after drug administration. We know that some drugs are administered as prodrugs that must be metabolized to the active drug. In this case, the drug effect may be delayed with respect to parent drug concentration in the central compartment. In addition, delay may occur due to some physiological turnover. The classical approach to model such delay in PKPD literature is to use a transit compartment model. It's described by this system ordinary differential equation. Now, ST denotes the signal to be delayed, S1, S2 to Sn at the transit compartment, and the kappa at the transit rate. The mean transit time is given by the ratio of the number of compartments to the transit rate. The transit compartment model can capture a variety of data very well. However, the obvious disadvantage of this approach is that one has to manually find a proper value for the number of compartments. It may also require many ODEs to fit the data, and it may not adequately describe some complex features. Now, our alternative approach is to use a delay differential equation to model delayed outcomes. Now, the difference between ODE and DDE is that for ODE, the future state of the system is totally determined by its current value. While for DDE, the future state of the system is not only determined by its current value, but also determined by its past value. The delay differential equations have been widely used in biological science and engineering to model delayed outcomes. The first biological application of DDE dates to 1920s when Walter investigated predator and prey interaction dynamics. However, this approach did not become widely adopted until 1970s. In recent years, we have seen DDEs starting to be used for some pharmacology applications. There are two types of delay differential equations. One is with discrete delay, and the other is with distributed delay. Now, for the discrete delay approach, it's assumed that the same delay time for all the signal mediators, such as cells or drug molecules, depending on what you are trying to model. While for distributed delays, the delay time varies among the signal mediators. This is particularly relevant in modern therapies such as oncology, diabetes, and arthritis. This is a simple differential equation with discrete delay. Now you can see that the future state of the system is not only determined by its current value, but also its past value. Now here this tau is a positive number. So because of this, you have to specify the value for S over the range of negative tau to 0. Now this S0 is often called history function. The discrete delay approach has been used in a variety of studies. For example, it was used by Banks Group in 2003 to model the HIV infection dynamics. The HIV infects CD4 T cells, and there are temporal delay between the time the virus infects the CD4 T cell and the onset of viral production. Now, in this HIV model, it's assumed that the length of the time from initial infection to the viral production is the same for all the CD4 T cells. Now, if I let ST denote the number for acutely infected CD4 T cell at time t, and tau is the delay time, then the number for CD4 T cells that can produce virus at time t is given by ST minus tau. Now we know that the assumption made in this HIV model may not be realistic because the delay time may vary among infected CD4 T cells. So how to accommodate this? We may use a weighted average of all the possible values for the delay time. Now, for example, if I assume the delay time for 20% for CD4 T cells is tau 1, and the delay time for 50% of them is tau 2, and the delay time for the rest of them is tau 3, then the number of CD4 T cells that can produce virus at time t is given by the sum of these three terms. Or we can take this one step further. If there are infinitely possible values for the delay time, then we get this conclusion for the probability density function of the delay time and the signal to be delayed. And this conclusion is called distributed delay. And the distributed delay is often thought to be more realistic than the discrete delay approach. This is a simple differential equation with the distributed delay. You can see that for this case, we have to specify the value of S over all negative t in order to define this differential equation. Now, I want to point out that the distributed delay includes the discrete delay as a special case. Now, depending on your data, you may find that you may need to use a gamma distribution or a variable distribution or inverse Gaussian distribution or some other distribution to better model the delay time. Now, in this talk, whenever I talk about gamma distributed delay, it means a distributed delay with the delay time assumed to be gamma distributed. The same thing applies to variable distributed delay and inverse Gaussian distributed delay. In case you are not familiar with the gamma distribution, here is a PDF for the gamma distribution. Now, it's characterized by two parameters. One is called the rate parameter, and the other one is called the shape parameter. Now for both parameters, the value can be any positive number. This gamma is denotes the gamma function. It's described by this integral. Now, if we assume that the shape parameter is a natural number, then the gamma function just reduced to this factorial function. I want to point out that the gamma distribution reduced to an Erlang distribution when the shape parameter is a natural number. So the gamma distribution includes the Erlang distribution as a special case. Now, the mean of the gamma distribution is given by the ratio of its shape parameter to its rate parameter. Now, this is a plot for the PDF of gamma distribution with the same rate parameter value, but different shape parameter values. Now, this curve is for the case when shape equal to 0.5, and this one is for the case when shape equal to 1. Now, these four curves here are for the case when shape is greater than 1. Now, this is one of the important slides in this talk. Now, if we assume the shape parameter of the gamma distribution is a natural number, that is a Erlang distribution, then the gamma distributed delay just reduced to this transit compartment model with this conclusion equal to the product of the transit rate and the last compartment. Now you can see that the shape parameter determines the number of compartments, and the rate parameter determines the transit rate. And its mean is just the mean transit time. Now for more information on this, you can refer to our 2018 paper. So you can see that the gamma distributed delay is just a natural extension of the transit compartment model. And the number of transit compartments is replaced by a shape parameter. Since the shape parameter becomes a regular model parameter, you can just estimate it along with other parameters. You can even add a random effect to it if needed. Now, except for some special case, the distributed delay has to be approximated through some numerical scheme. PML provides two functions to do that. One is called delay function. And this function was first introduced in Phoenix 7.0. It was exclusive use for discrete delay. And the history function must be 0. In Phoenix 8.0, this function was extended to include gamma distributed delay. And the history function can be any constant. In Phoenix 8.3, this function was further extended to include variable distributed delay and inverse Gaussian distributed delay. And the other way to implement distributed delay is through the gammaDelay function. And this function was first introduced in Phoenix 8.3, and it was exclusive use for gamma distributed delay. And the history function must be a constant. The difference between gammaDelay function and delay function is that is how the conclusion is approximated. Now, for the delay function, it involves direct numerical calculation of the conclusion with the value of the signal to be delayed recorded in a table upon every derivative evaluation. So the computational cost directly depends on the number of values recorded. So it can become very time consuming, especially in the case where the problem is safe. As the gammaDelay function was implemented based on the ODE method proposed by Professor Krasinski in his 2019 paper. Now, this function is usually much faster than the delay function. especially in the case where the shape parameter is greater than 1. So I want to point out that these two functions can also be used in our new product RS NLME. And this is a syntax for the delay function, as the signal to be delayed. Now, as I said before, this function can be used for both discrete delay and distributed delay. So now, if the shape option is not provided, then it's described by discrete delay, and it returns the value of st minus mean delay time. This mean delay time is given by the second argument. Now, if this option is provided, then it's described by distributed delay and returns this conclusion. Now, the D here is a PDF distribution specified by this option, and with the shape parameter specified by shape option, and the mean described by the second argument. Now, since this option is to use the specified distribution, so it's only used for the case where the shape option is provided. Now, the value of this can be gamma, y-ball, or inverse Gaussian. Now, if this option is not provided, then this equal to gamma is assumed. Now, this option, haste, is to use a specified history value of S. Now, the history value must be constant. And this is the most commonly used case in PKPD studies. However, the history value can depend on some variables that are defined at time 0 for the subject, such as the covariate, fixed, and random effects. Now, if the haste option is not provided, then it's assumed that the history value is just equal to 0. Now, this is the syntax for gammaDelay function. You can see that it has the same argument as the delay function, except the last one. Now, since this function is exclusive use for gamma distributed delay, so the shape option must be provided. It's used to specify the shape parameter of gamma distribution. And the second argument is used to specify the mean for the gamma distribution. The same thing, haste, is used to specify the history value, and it must be constant. And the last argument must be provided, and it's used to specify the number for ODE used to approximate the conclusion. Now, as I said before, the gammaDelay function was implemented based on Walter's 2019 paper. So in order to better understand this function, I just want to give you some very brief introduction to this approach. Now, the idea behind this ODE approximation approach is to use the binomial theory expansion on this term. And this is the puzzle formula for the PDF gamma distribution. Now, by using this, you can find out this gamma distributed delay can be written as the sum of these two terms. And here, I assume that the history is just a constant as 0, and the G is a cumulative distribution function of gamma distribution. So the first term is just used to account for the history part. Now, for the second term, this one is a generalized binomial coefficient given by this one. And the IJ satisfies this ODE. So to approximate this conclusion, you can just truncate this infinite series after n+1 terms. So this interval just approximated by some ODEs. Now, in Walter's paper, it was found that the approximation error is given by this one. So you can see that this is a shape parameter. Now, if the shape parameter is less than 1, then the approximation error decreases slowly as n increases. So we see that for this approach, the accuracy of the approximation depends on the number of ODE used. The higher the number of ODE used, the more accurate the approximation. However, the performance cost increase as number of ODE used. So we recommend doing some exploratory analysis for the effect of the number of ODE on the solution of the given problem. Now, here is a general guideline given by Walter's paper on the number of ODE used. If shape parameter is greater than 1, then n greater than or equal to 20 may be needed. Otherwise, n greater than 100 may be needed. Now, I'm going to demonstrate gamma distributed delay model through an example. And this example is an extension of a published transit compartment model given by this paper. And this transit compartment model was used to describe the delay process in the platelet production following dosing with the feedback mechanism. Now, in this model, there are 3 transit compartments, and KTR is a transit rate, and PLT denotes the platelet count, and the KL is a degradation rate of platelet. Now, this term is just used to describe the production rate of platelet precursor. Now, the KPR is a zero-order production rate, and the E denotes the drug effect. It's described by this sigma Emax model. Now, PLT0 denotes the pre-dose steady state level. So you see the production rate depends on the PLT itself. Now, this is a transit compartment model used in that paper. So I want to remind you again that this ST denotes the production rate, and is given by this one. Now, since PLT0 is a pre-dose steady state level for platelet, so you can find out that the history value for S is just equal to KPR. Now, based on what we discussed before, if C is a big PDF or gamma distribution, with the rate parameter being KTR and the shape parameter being 3, then this term is just equal to this one. So in order to extend this transit compartment model to a gamma distributed delay model, I simply replace this one and all this stuff by using this one. Now, for this gamma distributed delay model, and the shape parameter for the gamma distribution is allowed to be any positive number and will be estimated along with other parameters. Now, for more information on this extension, again, you can refer to our 2018 paper. Now, here I want to show you how to implement this gamma distributed delay model in PML. Now, this is a code for this one. Now, if you want to use the gamma delay function to approximate this one, then this is the corresponding PML code. Now, as I said, the history value for S is a KPR. That's why you set hit equal to KPR. And for this problem, we found that 61 ODE is needed. Now, this one is just used to describe this differential equation with distributed delay. Okay, and this one is just used to specify the initial condition of PLT at time 0. Now, if you want to use delay function for this one, then you can just simply replace this one by this one. Now I'm going to fit this gamma distributed delay model using some simulated data. And the data was simulated using the original transit compartment model approach, with number of platelets simulated for 78 subjects every 24 hours during the time frame for 648 hours. And this gamma distributed delay model was fitted in Phoenix 8.3 using the FOC ERS engine. And the value of all PK and some PD parameters are fixed to the one used to generate the data. Now to see if the shape parameter can be recovered from the data, and the initial value for all the estimated parameters are chosen away from the true value. And these are the results obtained for fixed effect by using either the gammaDelay function or delay function. Now, this is the estimate obtained by using gammaDelay function, and this is the estimate obtained by using delay function. You can see that the estimates are very close to each other, if not the same. In addition, you can see that for the shape parameter, the estimate is either very close to its true value or the same as the true value. In addition, you can see that the CA percentage is less than 2%. Now for all the other parameters, you can see that the estimate is similar to its true value. And also the CA percentage is less than 5%. Overall, you see that the model using gammaDelay and delay functions give very similar estimation results with estimates close to true values. In addition, we also see that the shape parameter can be reliably estimated along with other parameters. Now, using the same setup, running on the same Windows desktop machine with 1.8 GHz, and the total running time for the model using the gammaDelay function is just about 9 minutes, while the one for the delay function was 25 hours, 30 minutes. So you'll get a huge time saving by using the gammaDelay function. In conclusion, gamma distributed delay model is a natural extension for transit compartment model. It avoids manually finding a proper value for the number of compartments. Now, the ODE approach proposed by Walter 2019 paper provides a much faster way in numerically computing the gamma distributed delay. Now, even though this approach can be manually implemented in any PKPD software, the gammaDelay function allows single-line code specification, so it's more efficient and less error-prone. Now, even though the delay function can be used to implement variable distributed delay and inverse Gaussian distributed delay, it can become slow, just like for gamma distributed delay. So a faster numerical algorithm for distributed delay with other distributions are still needed. Okay, this is the end of our talk. Thank you very much for your attention. Anna, do we have any questions?
Yes, thank you very much, Dr. Hu, for a great presentation. We do have a couple of questions coming in, and please, if you have any questions, type it in the Q&A panel. Okay, let's get started. The first question is the variable distributed delay also very slow? And if it is, are there any plans to implement a variable delay function in PML?
the variable distributed delay was implemented in PML through the delay function. So it used the same numerical scheme as the gamma distributed delay. So yes, it can become very slow, just like for the gamma distributed delay case. Now, in Walter's 2019 paper, it suggests that the binomial series expansion trick may be able to work for variable distributed delay. However, further research is still needed. So I hope that with more researchers involved on this, we can find a better and fast way to implement the variable distributed delay in the near future.
Great, thank you. Another question that just came in: does the history function in history function in the gamma delay, does it have to be constant?
Yes, right now the history function must be constant. Yes, for the current release. Yes.
Okay, great. A couple more questions if we have time. One is, can delay and gamma delay functions be used for absorption delay case? How is the dosing information then incorporated in these functions?
Okay, so for both delay and gamma delay function, they cannot contain dosing information from the input data set, so they cannot be used for absorption delay case. I want to point out that for this special case, the distributed delay reduced to some linear combination of the PDF delay time, which depends on the dosing information from the input data set. So for such case, there's no need to use some numerical scheme to approximate. This means that you can manually implement. However, we do know that this may become very difficult and error-prone, especially for the multiple dosing case. And because this PML provides a special statement called delay in CPT to model absorption delay case. And this statement was first introduced in Phoenix 8.0. It's exclusive use for the case where delay time is assumed to be gamma distributed. In Phoenix 8.3, this statement was extended to include not only gamma, but also variable and inverse Gaussian distribution.
Thank you. We do have a couple more questions. There's a question about when is the delay be available in WinNLN. I'm assuming that means in Phoenix, which this is already available. Is that correct?
Yes. So PML is a pharmacometric model language behind the Phoenix. So because all these functions implement in PML, so yes, they can be used.
Okay, I think we have time just for one more question, even though we might have a few more in the Q&A, and we will respond to those when we provide the recording. Last question is, at the beginning of your presentation, you mentioned RSNLME. What is RSNLME product about?
So RSNLME provides an interface to access to the Phoenix NLME engine. It allows users to define PKPD models in R. It also allows users to perform estimation simulation in an R environment with a capability for parallelizing the runs using multiple MPI or grid. RSNLME also provides a novel Shining app to facilitate the process for model building and model execution. So once the flexibility for the RSNLME provides is that the user can use some other open source package to do some post-processing or pre-processing of data, etc. So
thank you. Actually, one more question just came in. I'll just ask that one quickly. Do we need to prepare the data set differently to use the delay function in Phoenix version 8.3?
No, it's just like for the other model. That whatever Phoenix is the requirement required by Phoenix is the same thing as for the distributed delay model.
Excellent. Well, thank you very much for this presentation, Dr. Hu. Thank you, everybody, for attending, and we will be adjourning now. Thank you.
Yeah, thank you.